Bismillahirrahmanirrahim. In these lectures, lecture number 15 and 16, we will discuss elasticity matrix for trigonal, tetragonal and for hexagonal. Up to now we have discussed triclinic, monoclinic, orthotropic, cubic and isotropic continuum. We have discussed these continuum in similar way, but we will discuss these three continuum in a different manner. In both cases means that when we are discussing the previous five continuums and these three continuum, our purpose is to find the elasticity matrix for these continuum. Elasticity matrix which represents the elastic properties of continuum. Here we will follow the different procedure. These three continuum, trigonal, tetragonal and hexagonal, will be discussed in similar fashion. So from start these three are same, that we have common things from the start for these three continuum. You can see that for trigonal we have written n is equal to 3, for tetragonal we have written n is equal to 4, and for hexagonal we have written n is equal to 6. What does this mean? You know that, if you remember, that we have n-fold axis of symmetry which is denoted by a n subscript of capital A. So that n-fold axis of symmetry means that we have rotation about an axis with an angle of 2 pi by n. So when we will talk about trigonal, so it means that we have angle of rotation 2 pi by 3. Similarly for tetragonal we have 2 pi by 4, and for hexagonal we have 2 pi by 6. So there is one an axis in each elasticity, trigonal, tetragonal and hexagonal. Suppose that axis is parallel to x3 axis, or x3 axis is parallel to that an axis. So when we say that x3 is parallel to that axis, it means that x3 will act as axis of rotation. So now we have to write transformation matrix for that axis of rotation, which is x3. It will be this 0 0 0 0 1 and cos phi sin phi minus sin phi cos phi. You can have this from your coordinate transformation. You can write this matrix from your coordinate transformation. Now what we have to do now, basically we have to diagonalize this matrix A for the purpose to find the elasticity matrix for these three continuum. Now you must know about the diagonalization before this, so you need to revise your linear algebra, in which you have to study the topic of similarity, then diagonalization. That when two matrices are similar, if you have matrix A and matrix B, suppose both have order n by n, then we say that they two are similar, that A and B are said to be similar if we have B is equal to S inverse AS, that S is any non-singular n by n matrix, that there should be a non-singular S matrix of order n by n in such a way that B should be equal to S inverse AB. Then we will say that A and B are similar with each other. When these are similar each other, that when A and B are similar with each other, then their eigenvalues are same. This is the characteristic of similar matrices. Similarly, when you talk about the diagonalization, that if your matrix A is similar to a diagonal matrix, then we will say that A is diagonalizable matrix. So there is also a theorem that matrix A with order n by n is diagonalizable if and only if A has a set of n linearly independent eigenvectors. This is a property, that if a matrix has n of order n by n has n linearly independent eigenvectors, then you can diagonalize that A matrix. Let's see how we can diagonalize this matrix A. First, we had to calculate its eigenvalues. Its eigenvalues are these. We have to calculate its eigenvalues, and we will say that the matrix, when we have diagonalized this matrix A, then that matrix has eigenvalue the same the eigenvalues. Now this is the process which you already know. Cos phi minus lambda sin phi 0 minus sin phi cos phi minus lambda 0 0 0 1 minus lambda is equal to 0. This is the characteristic equation. After this you have this, and you will open this determinant from third row. Then you have this. The one eigenvalue is this, and second and third eigenvalues are lambda is equal to e power iota phi and e power minus iota phi. Now we will calculate the eigenvector for this matrix. For lambda 1, you have this, you can write this. This is cos phi minus 1 sin phi 0 minus sin phi like this, and 1 minus 1 0. So you can have this cos phi minus 1 into x1 plus sin phi x2 minus sin phi x1 plus cos phi minus 1 x2 is equal to 0, and from here you can see that x1 and x2 is equal to 0. This is a homogeneous system. No, from third equation you have 0 x1 plus 0 x2 plus 0 x3 is equal to 0. It means that x1 and x2 are 0, but x3 is arbitrary. So we let that x3 is equal to 1. The eigenvector, no, you can write this eigenvector 0 0 1. Now for second eigenvalue, for lambda is equal to e to the power iota phi, we have this cos phi minus e power iota phi sin phi minus sin phi cos phi minus e power iota phi. After calculating this, you have this, and from here you can see that x3 is equal to 0. x3 is equal to 0, because here we will write 1 minus e to the power iota phi. x3 is equal to 0. the coefficient of x3 will be 1 minus e power iota phi. So in that case x3 is equal to 0. So product of two things equal to 0, one thing must be equal to 0, so we have to take x3 is equal to 0. So from here you can write this, and from here you can from here you can write this, and it will be x1 equal to minus x2. These are simplifications. You can do this by yourself. You can't you are allowed that you can't follow my steps, that what I have done. So you need to simply calculate the eigenvectors with the given for given eigenvalues 1 iota per phi iota per minus phi. So simply follow the procedure which you follow in your previous classes. So no need to follow whatever I have done here. But at the end you have this type of eigenvector for your this type of eigenvalue e power iota phi. That would be 1 iota 0. So we will normalize this eigenvector here. It would be 1 over iota 1 by square root of 2 iota by square root of 2 and 0. So here no need to normalize because length is 1, so it would be 0 0 1. So now we have to calculate two eigenvectors for 1 and for e power iota phi. Now we will calculate third eigenvector, which is e power minus iota phi. So it would be this. So x3 is equal to 0 again from these two equations we have x2 is equal to minus x1, and you can write this. Then your eigenvector is iota 1 0. So this is the normalized eigenvector. Now this is the matrix B, which we can write from these three eigenvectors. This is the eigenvector, one eigenvector, this is the second eigenvector, and this is the third eigenvector. That we have written this B similar as we have our A, similar in the fashion that third row and third column there is 1, other are 0 0. Now what is this? Here we have calculated B, dagger of B dagger. Now what does this B dagger means? That if your matrix is real, then you simply calculate its transpose. Now here we have iota complex values. Then you need to calculate first its what we see that iota bar is equal to minus iota. What is that? That when we take bar on these, we have 1 by square root of 2. This is minus iota 1 minus iota by square root of 2. This is 0. This is again minus iota over square root of 2. This is 1 by square root of 2. 0 0 1 and 0 0 minus 0 0 plus 1. Sorry, conjugate. that bar is get conjugate. I have forgotten that word for conjugate. So a plus iota b, when we take the conjugate, then we write that a plus iota b equals to conjugate of a plus iota b equals to a minus iota b. Sorry that I have forgotten the point, then word for that. Then we take the, after conjugate, then we have to take the transpose, and it would be this. No, this is for diagonalization. Here we have B dagger. This is your given matrix A, and this is your B. Same as I have said in the definition for the similar matrices, where we have S inverse. In this we have also used the orthogonality. That is why here we have B dagger. That if you know that if matrix is orthogonal, then orthogonality means A transpose is equal to identity. So A transpose is equal to A inverse. That means that inverse and transpose of that matrix is similar. So either you can write A inverse or transpose, result will be same. So here we have B, but in this B we have complex values. So instead of simply take transpose, we need to take also the conjugate of these values. So simply here we have not transpose, but also we have written here dagger, B dagger AB. Why? Because B is complex matrix. If B is not complex, then we simply write here B transpose AB if B is orthogonal. When we do all these simplifications, we have, it is up to you that whether you multiply these two first or these two first. I have multiplied these two first, and then we have this is similar, and then we have this, and after this when you multiply this, you have this thing, and you can write this e power iota 5 by 2 plus e power iota 5 by 2 1 by e power minus 5 plus 1 by 2 e power minus 5 0 1, and this would be e power iota 5 0 0 e power iota minus 5, then 0 0 1. Now this is the diagonal matrix. Now this is from the definition of diagonalization, that if your matrix is similar to a diagonal matrix, then we see that it is diagonalizable. Now your matrix, our matrix A, is similar to this diagonal matrix, and also you can see that eigenvalues are, it means that A and this matrix is similar with each other. So eigenvalues are, these two must be same according to the definition of similar matrices, property of similar matrices. So you can see that you have written your B, in which you have written this eigenvector first, and this is corresponding to e power iota 5 plus iota 5. So your first eigenvalue is this, and you have written this at the second, and then your second eigenvalue is this, and this is your third. So your third eigenvalue is this. Now further we will use this matrix to study the elasticity matrix for the continuum. So in the next lecture we will start that how we will make use of this matrix and then matrix B or matrix given matrix A to study the result for elasticity matrix for isotropic continuum. Now what you have done now, you have studied diagonalization and similar matrices with orthogonal matrices from your linear algebra of any linear algebra book which we use in our BS classes. So thank you so much.